Right. Stereoisomerism, we have to categorize them into three parts. One is geometrical isomerism, conformational isomerism, then we have optical isomerism. See, first look into geometrical isomerism. Geometrical isomerism to occur, we must have something called restricted rotated system, restricted rotation system, which means you should not be able to rotate the bonds easily between two reference atoms. For example, if there is a C double bond C, N double bond N, C double bond N, and C single bond C in a cyclic structure, all of these are restricted bonds. You cannot rotate them freely. What I'm trying to say is like this. Suppose if you have a methane, have carbon and three hydrogens here like this. Now this can be rotated freely. Nothing will happen. CC single bond is easy to rotate in an open chain. Why? Because the sigma bond forms like this. And if you rotate the sigma bond here, the overlapping is not disturbed. So you can keep on rotating like this. The overlap will not get disturbed. But if you have a double bond, if you try to rotate, the bond will break. Correct? The bond will break here. Therefore, double bond cannot be easily rotated around. Second thing, the distance between the group across the RRS, that means rotation restricted system across the RRS, if the distance between any two reference groups are different, for example, methyl have a distance y units here, and here methyls have a distance z units here, and you know that there is a restricted system across these 2 points. In that case, you can clearly make out that the distance y is longer than z, which means then I can say these two are geometrical isomers. Okay. So to convert a geometrical isomers to one another, bonds must be broken. So how do I convert this to this? Say, how to break this carbon-carbon bond, I have to break this carbon-hydrogen bond, and I have to remake them by making their spatial orientation different. And that's how you will get this as, y being greater than z. Okay, clear? Notice geometrical isomerism across C double bond C here. You can see hydrogen on the same side, and this hydrogen are on the opposite side. If I want to make it rotation freely, this pi bond is completely converted into dot and dot. It will become a single bond. On rotation here, then it will start changing its positions, and that's how you can end up getting this double. So from cis, if you want to go to trans, I have to break the bonds only and then go. These type of changes between two groups is what we call it as geometrical isomers. Generally, trans form is more stable than cis due to its steric repulsions. Okay. Now, before going into further details of it, I want you to first figure it out whether whatever the examples which I'm writing, if there is any rotation restricted system and if there is any geometrical isomers that you can observe. Okay, so check out examples. Find any geometrical isomers existing in the system. Okay, so I'll write the structure. You can write it in your own notes as well. Double bond here with methyl and methyl, the first case. Second case, double bond here with methyl and methyl. CH3, C triple bond here with CH3. Next, I have OH here, OH here, double bond CH2. Next, NH2, sorry, NH, double bond NH. Okay, CH2, double bond CH, CH, double bond CH2. Next, in case if you have methyl here, ethyl here, and a double bond here like this. Okay, next. In case, sorry, in case if you have only methyl and methyl here, if you have methyl here and a double bond here, in case if you have a methyl and methyl here and double bond here. Okay, please check these cases. Tell me which of the cases you can find that they can have geometrical isomers, which does not have geometrical isomers. Okay, so take a minute's time and solve all of them. Check out in the first case. In the first case, answer is no. There will not be any geometrical isomers existing. Here you will not have any geometrical isomers existing. Why? Let me explain. There is a definitely rotation restricted system here. Very good, no problem. Then there is a methyl group here. There is a methyl group here. The distance between these two is, let's say, x units. Now tell me, is there any other alternative by which we can remove this methyl and this methyl group, put it in a same location with a different distance here? Answer is no, because of this double bond. Now this methyl and methyl group are only having one orientation to align. So this is the only orientation on which we can keep the methyl group. What I'm trying to say is I cannot have something like, the ring is breaking here. From here, the ring is making, and methyl is coming somewhere here like this. And now the distance between these two are changing. This cannot be done, right? Because six-membered ring, I cannot have something like this bond breaking and it can attack from somewhere else and the ring will change like this. That is not possible. Since this type is not, since this type is not possible, this type of thing is not possible. That means you can have only one form, that is cis form. So let me write down that only cis form exists. Only cis form exists in that. Second case. Well, now if you notice the second case here, we will have this as, double bond with two methyl groups here, methyl and methyl. Now problem is this side, if at all I have a distance between two methyl groups. Now here I have a methyl, here I have a methyl. Let's say this is x distance. Now if at all I change that methyl to the other direction here, here also I am getting a methyl only at the x distance, isn't it? So that means whether you change the orientation, it doesn't make any difference. Still it is going to be x distance, which means one important criteria is that across a rotation restricted system, the carbons must have at least two different groups. They cannot have same group. If they have same groups, they cannot show geometrical isomerism. That's why even this will not show geometrical isomerism. Yeah, I guess this part is clear. Okay. All right. See the next one. Here also you can have, if you have a triple bond, although it is a restricted system, it cannot showcase any geometrical isomerism. Here also this carbon has two same groups, two hydrogens, which means it cannot show any hydrogen bond, any double bond, geometrical isomers. Here it can show, reason being, nitrogen double bond nitrogen we have. One side we have hydrogen, the other side we can have lone pair. Hydrogen and a lone pair. And if at all I change their position like this, now you can notice the distance between the hydrogen has changed. Here the distance between the hydrogen is this much. Here the distance is like this. So you can see there is a difference in the distance, which means yes, this can show geometrical isomers. Again here along this double bond you have two hydrogens, no geometrical. Here also there is no geometrical. So that means no and no here. Next here also double bond. There are two hydrogens at this end. That means no geometrical isomers. Now notice this one. Here we can show geometrical isomerisms. Why you know? First of all, I told you that ring, even if you have a single bond, it is restricted. And now I can put these two groups, these two methyls coming away from the out of the plane, or I can keep one out of the plane and one inside the plane. So that means if this is, same side, the distance will be lesser, which we call it as the cis form. And then this one will become the trans form of it. Hence, here we can see there is a geometrical isomer appearing. Same logic goes to this one also. Geometrical isomerism is not with respect to this double bond, but with respect to the restricted system at this position and this position. At these two positions, there is a restricted system. How does that restricted? Like this. You can have group coming out, methyl here, and one group coming out here like this with a double bond on it. Okay, double bond on it here like this. Or I can have this group going inside with a methyl group and this group still coming outward with a double bond here like that we can have cis and trans isomers. Same logic applies to here, not with respect to this double bond but with respect to these two methyl groups. With respect to these two methyl group, again I can have geometrical isomers. Clear? All the cases are clear, everybody? Right. Next, check out geometrical isomers in cumulines. Cumulines means if you have a continuous double bonds, that is called cumulines. In that, if you have one, two, three pi bonds continuously, then this groups will be on the same plane. On the same plane, now you see R1 and R1 are at this distance. Now R1 and R1 are at this distance. So distance are different. Hence, if this is cis, this has to be trans. Likewise, if you keep on adding odd number of pi bonds with this will always generate a planarity, thus giving two geometrical isomers. So here also you can see 1, 2, 3 odd number of pi bonds. Hence they can show cis form and trans form. This I just told you. If you have a double bond across the cyclic structure, only cis exists, no trans exists. This also I just discussed with you. Now notice the next one. If you have cyclooctene onwards, that means before 6 cyclooctene, that means up to carbon 7, we cannot have a trans form existing. We can only have cis form. But 8 onwards, we can also have trans form. You can see this is a cis form. The trans structure will be like this. There is a double bond here, and then there is a group that is going to change like this. So that's how you can get a trans form. So this is cis, this is trans. So you can see here the groups are opposite to each other. Then we have decene. A double bond here is cis, a double bond here is trans. So we can have cis and trans isomers. So you can see 8 to 10 generally the cis isomers are more stable than trans. 8 to 10. 11 onwards the trans is more stable than cis. Very important, everybody. Remember 8 to 10 cis isomers are more stable in cyclic structure. 11 onwards, trans is more stable than cis isomers in cyclic structure. And notice that stability usually depends upon heat of combustion per CH2 unit. Okay, that's the experimental way of judging which one is more stable or not. You have to check per CH2 how much amount of heat of hydrogenation we are getting. Here you can see this is a cis form, this is a trans form. Trans form is more stable. See the ring size here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 membered ring. So 14 is of course greater than 9. So this will have more stability in trans. In cyclic structure, I told you just now, if you have two methyl groups, they can be on the same side or they can be on the opposite side. So X is not equal to Y, so this can exist. This also I just told you. One is going up, both are going up, or one going up, one going down. That makes it cis and trans isomers. This one also I told you, like Cl is going up here, this one group is coming down, or both of going up. That will show cis and trans isomers. Now it doesn't matter, it has to be same group. You can have two different groups also, still we can call it as cis and trans isomers. Geometrical isomers in N double bond N. I just told you N double bond N can have cis and anti. Instead of using the cis and trans, now you use two different terminologies. We call it as syn and anti. Syn isomer and anti isomer. Okay. So anti isomer is generally more stable than syn isomer. Okay. Similarly, geometrical isomer along C double bond N. See, if you have C double bond O and NH2, this will be removed as water and you'll get this as C double bond N. Achha, C double bond N has hydrogen and OH group on it. Then we call it as aldoxymes because it is coming from aldehyde and hydroxylamine. So aldoxyme. So you see aldoxymes, hydrogen and OH are on the same side, it is syn isomer. Hydrogen and OH are on the opposite side, it is anti-isomer. Same way, this is syn, this is anti. So you can see this is anti, this is syn isomer. If you have two different alkyl groups, that is called ketoxime. In ketoxime, you can read it like this. If this methyl and OH are on the same side, you call it as syn methyl ethyl ketoxime. Or I can read it as ethyl and OH are on the anti form. So you can write it as anti ethyl methyl ketoxime. Okay. So you need to check out with respect to OH and then read it accordingly. So you can have both the names here. Same way, phenyl and OH are on the same side. So syn phenyl methyl ketoxime. Methyl and OH are on the opposite side. So anti methyl phenyl ketoxime. These are the names to be used. Okay. Next, check out geometrical isomerism in triphenyl and tetraphenyl group. Okay. So you can see if you have a cis and trans form here, basically methyl and methyl are close distance. Here methyl and methyls are far distance. So that's why it is cis and trans. Trans because they will have less repulsions. Trans is more stable than cis. Here in this case, there is this form is cis. Why? Because this methyl and this methyl are on the same side. Here you can see this methyl and methyl are on the opposite side. So this is trans isomer. Right? This is in triphenyl or tetraphenyl structures. Next, in geometrical, in resonating structures, if you have a minus here, I can make a double bond with O minus. So you can have this O minus here. This H and methyl can be exchanged. You can get cis and trans isomers in this case. And lastly, geometrical isomers in decalin. In decalin, you can see decalin means 10 carbons in this ring structure like this. Here we can have two hydrogens on the same line or one hydrogen up and one hydrogen down like this. So we can have cis and trans isomers. This is basically how it looks like. Usually again, trans is more stable than cis in this case. Okay. Now, these are the cases you need to check out whether they are showing any geometrical isomers or not. Clear everybody? Okay. So guys,